Now let's quickly do question number 5. So in question number 5 we need to, so we have a sample of 400 golfers in the USA, and we have their height and gender information. And we need to actually do a 95% confidence interval for mean of height, and then 95% confidence interval for population proportion. And we have two hypothesis testing. So one is one sample test, and the second one is when we have two samples, when we want to compare male golfers versus female golfers. So for the first one, let's actually go one by one. So I'm going to start with a 95% confidence interval for the mean, population mean. So if you go to the formula sheet, so this is what we should be looking at. 1 minus alpha percent confidence interval for population mean. So we have the interval, formula for interval, and we have the Excel function for calculating t-value. So indeed, this one, only this one, confidence interval for population mean, Excel actually, let me actually do something. Let me go here. So 95% confidence interval for population mean. So this would be, so we have a population, so we have a big population. So these are golfers in USA, and we are looking for mu, population mean, and P either F or PM, population proportion of females, population proportion of male. So these are population proportion. But it would be hard to get these population parameters. What we do actually instead is that we take a sample of 400 golfers. So it's a sample, and instead of mu we can actually calculate a point estimate for mu, which is sample mean. And instead of population proportion, we can actually find an estimate for that, which is P bar F or P bar M, which is sample. So you see this bar? This actually means sample. Sample proportion of female, sample proportion of male. So it's very important not to get these confused. So we have this P actually stands for proportion of female, proportion of male. Later on, when doing hypothesis testing, we have a p-value. That one actually is probability value. So this is proportion, the other one is probability. Don't get this too confused. So now 95% confidence interval for population mean is, so the point estimate would be x bar plus n minus margin of error. Margin of error is t value, t half of alpha with n minus 1 degrees of freedom times standard error, which is s on square root of n. So this is a standard error. This is t value. This whole thing is margin of error. Indeed, so we're actually coming up with estimation for mu, population proportion. So our estimation would be x bar in the middle, and then we add margin of error to x bar, and that would be our upper limit. We subtract margin of error from x bar, and that would be our lower limit. So that's what I mean by finding the confidence interval. You have to find upper limit and lower limit, and in order to find those two, it's sufficient to find point estimate x bar and margin of error. So margin of error plus x bar, upper limit, margin of error minus, point estimate minus margin of error would be lower limit. So let's just go ahead and do this. In Excel, actually, instead of calculating all these things, all of them, t-value, standard error, everything, you can actually go ahead and use descriptive statistic tool. So you can actually go ahead and use descriptive statistic tool, which will give you x bar and margin of error. Margin of error here in Excel is called confidence level. So if you go to Excel, question 5, so 95% confidence interval for population mean of height of golfers. So 95% confidence interval for population mean of height of golfers. So we can actually, like I said, go ahead, use data analysis tool pack, descriptive statistic, and then we just need to make sure that we select C2 to C401, so our height column, and column is checked. Nothing, I didn't take C1, so I don't need to check label in the first row. Output range, I can put it here. The output, I'm gonna put it in B3. Sorry, this should be this. And then output range would be B3. And then summary statistic will give us mean, and confidence level for mean will give us margin of error. So if you click here, so these are the two numbers that we're looking for, mean and confidence level 95%. So therefore, point estimate, upper limit, and lower limit. So I'm gonna actually, I don't know why these are red font. I'm gonna make sure that all the page is in black font. So I'm gonna remove this one. So let me also show you the formula that I'm gonna use. So point estimate for population mean would be equal sample mean. Upper limit would be point estimate plus margin of error. Lower limit would be point estimate minus margin of error. For the next part of this question, we're looking for 95% confidence interval for population proportion of male golfers. So let me put it here, 95% confidence interval for population proportion of male golfers. Yeah. So when we go to our formula sheet, this is the part that we should be looking at. 95% confidence interval for population proportion. So this would be the formula. Let me just write it down again here. For population proportion P, population proportion, sorry. So for population proportion P, the 1 minus alpha percent confidence interval for P would be population proportion would be point estimate P bar plus and minus margin of error. Margin of error now is z half of alpha times standard error, which is P bar 1 minus P bar divided by n. So this is a standard error. Standard error, this is z value. This is z value. The whole thing is called margin of error. So for this one, we need to calculate P bar, we need to calculate n. So we have P bar, we have n, and then z value. So three things. And then we can go ahead and calculate margin of error and confidence interval. So if I go back to my Excel sheet, so I need to find sample size, and I need to count males, and then once I have number of male golfers, I can go ahead and calculate sample proportion of males. And after that I have P bar and just fix this. So after that I have sample size and sample proportion of male here, sample size n and sample proportion P bar. I just need to find I mean, with n and P bar, I can go ahead and find standard error. And then I need to calculate z value. And after that, I have z value and a standard error. If I multiply them, I can get margin of error. And after having margin of error and point estimate, I can go ahead and do point estimate, upper limit, and lower limit. So let me quickly show you the formulas that I'm gonna use. So for sample size, I'm gonna count my sample. My sample starts from second row all the way to the 401. So count A C2 to C401 would be my sample size. Count of male would be count if in column B, if equal to male. So I just type male here. 300, so 300 out of 400 are male, which means that 75% of them are male. The sample proportion of male is 75%. Standard error, so I just need to apply this function, square sqrt of p bar times 1 minus p bar divided by sample size. That would be my standard error. And then z value, the formula for z value is given here. Normal, standard, inverse, 1 minus half of alpha. So it would be equal norm dot s dot inverse 1 minus half of alpha. Alpha is, I mean, in our exams, in our questions, we always assume alpha is 5% unless otherwise stated. So here is 5%. So since we're looking for 95% confidence interval, 95% is 1 minus alpha percent. So if 1 minus alpha is 95, alpha would be 5%. So this would give us 1.96. Therefore, margin of error would be z value times standard error would be 0.04. So point estimate for population proportion would be 75. Upper limit would be point estimate plus margin of error. Lower limit would be point estimate minus margin of error. So now I can say with 95% chance population proportion of male golfers is between 71 and 79%. That's what I get. With 95% chance, population proportion of male golfers is going to be between 71 and 79%. So that's the answer for the second part of question 5. So let's move on to the third part. There is a claim that proportion of female golfers now, is above 20%. So let me just go back here. So we have the statement that we have is that the proportion of female golfers, is greater than 20% or simply 0.2. So this is a claim, so we just put it in alternative. So whatever is claim, if we have a claim, if we hope for something, we just put it in alternative. And whatever is left, we put it in null hypothesis. So PF greater than significantly or strictly greater than 20%. So null would be PF less than or equal to 20%. That would be our hypothesis set. So for this one, if you go to the formula sheet, you will see that this is the one. The test statistic is given here, and then p-value lower. You know exactly what would be the function. So that's the idea. The only thing that we need to do, let me just write it again. Test statistic, test stat for this hypothesis set would be P bar of F, which means sample proportion of female minus hypothesized value divided by hypothesized value times 1 minus hypothesized value divided by n. And hypothesized value here is 20%, this number. 20%. The number that it's on our hypothesis, the number that we want to test if it's equal to it or not. So that's our test statistic. And then after that we calculate test statistic, we need to calculate p-value, lower tail, upper tail, and two tail. P-value, lower tail would be norm dot s dot, it's given, the formula is given in the formula sheet here, actually, normal dot standard distribution of test statistic and true. So that's what I'm gonna do. Norm dot s dot dist of test stat true. So this is lower tail. Upper tail would be 1 minus lower tail, and then two tailed would be 2 times minimum of lower tail and upper tail. So now we just need to go back to our Excel file and calculate. First thing is to write down the hypothesis set. So let's go back. So part 3, null hypothesis would be that P of female less than or equal to 20%. An alternative would be that P of female strictly greater than 20%. So that's number 1. So the next step would be to calculate test statistic. For test statistic, we need to find, so this one is given to be 0.2. This one is sample proportion of female, and this one is the formula of standard error. So let's go ahead and just do this. So sample proportion of females, and then hypothesized value, and then standard error, After that we have all of these, we can go ahead and calculate test statistic. And once we have test statistic, we can go ahead and calculate p-value lower, p-value upper tail, and p-value two tail. Sample proportion of female. So let me just copy the formula so you can see what I mean here. So sample proportion of female. We already calculated sample proportion of male to be 70%. So 1 minus 70%, sorry, 75%. 1 minus 75% would be 25%, which would be the sample proportion of females. Hypothesized value, we're testing to see if it's greater than 20% or not. So we put 20% here. Standard error would be square root of P0 times 1 minus P0 divided by sample size, and sample size is 400. We calculated it earlier, so I just used that one. So test statistic now. If you look at the formula, test statistic is sample proportion minus hypothesized value divided by standard error. So it would be parentheses sample proportion minus hypothesized value divided by standard error. So this is gonna give us 2.5. Now we just need to find p-value lower, upper, and two-tailed test. So p-value lower tail, if you go look at the formula sheet, this is the formula that we need to use. So norm dot s dot distribution of test stat, and for cumulative just put true. P-value upper tail would be 1 minus p-value lower tail, and p-value two tail is going to be 2 times minimum of these two guys. So this would be the p-values now. Now the last step of hypothesis testing would be to pick the right p-value. So this is definitely a one-tail test, and it's a upper tail test because we are rejecting at upper tail. So when we want to reject this statement, the null hypothesis statement, we take a sample. If the sample proportion is significantly greater than 20%, is significantly larger than 20%, we can go ahead and reject this statement. So therefore we reject at upper tail or right tail of the distribution. So therefore this would be an upper tail test, and we take p-value upper tail. And now we compare this to alpha. The rule was reject null hypothesis if p-value is lower than alpha. So we reject null hypothesis because p-value is lower than alpha 5%, and conclude that, what would be our conclusion? I conclude that P of female would be greater than 20%. So we reject null hypothesis, this one, and take this one with 95% confidence, and conclude that P would be greater than 25%, would be greater than 20% with 95% confidence. That's what we do. Now the last part of the question 5, test if the height of male golfers is significantly greater than female golfers. So this is what we want to test. Let me just come here. So we want to test the mean height for female golfer thing that we want to test is that we want to test if mu male minus mu f is greater than or equal to 0, right? So we, or mu m greater than mu f. Indeed, there is no this. Just remove this. This would be indeed our alternative hypothesis, because this is something that we want to be sure about, right? We want, so when we take a sample, we want the sample that corresponds to the male population to have a significantly greater mean than the sample that corresponds to the female group. So we take this as alternative, and then null would be mu m minus mu m minus mu minus mu f less than or equal to 0. So this would be our alternative. This would be our hypothesis set. So I'm just gonna go ahead and write it down. Part 4. Null would be mu males minus mu female, less than or equal to 0. An alternative would be mu males minus mu females to be strictly greater than 0. So that's what I want to do. And as you can see here, we are dealing with two samples, right? One sample from the male group and another sample from the female group of golfers. So what I'm gonna do, I'm gonna use t-test two samples, t-test a two sample test with unequal variances. And the reason I'm using unequal variances is because I have only two options, equal variances or unequal variances. And unequal variances actually would be safer. When we use unequal variances, we're not actually imposing any assumption on variances. So basically it would be safer. But when I use these two, when I use the t-test two sample assuming unequal variances, I have to give two columns. So one for variable 1 range, like male, one for female. But it's now not organized in this sheet. So I have to organize it. One way that I can do it is basically just sort this Z to A. And now I have my males on top and female at the end of my table. So now I can go ahead and use data analysis toolpath, t-test two sample assuming unequal variances. Okay. So variable 1 range, the height of male people, just go down. I just go down and I make sure that I take all the male in my sample. Okay. 300 male and then 100 female. So C2 to C301 for male, C302 to C401 for female. Hypothesized mean value would be 0. There's no labels. Alpha would be 5% again. Output range, I check here and I put my result here, E56. So this is definitely, this is a one-tail test. It's actually an upper tail test. So if you remember, this tool only gives us p-value one tail, but in order to see if it's p-value upper tail or lower tail test, p-value upper or lower tail, you just need to look at the test stat, and if test stat is positive, this is upper tail p-value, upper tail p-value. And that's exactly what we're looking for. We have an upper tail test and we have p-value upper tail. So we just take this number, compare it to 5% alpha. Since this is significantly lower than alpha, we say since p-value is lower than alpha 5%, we reject null hypothesis and conclude that we take this one alternative. We conclude that mean height of male golfers is significantly greater than female golfers, and we make this conclusion only with 95% confidence interval. 95% confidence level. That would be it for this question. So this actually answers question number 5.